light. So everything was based off of light energies, light energies, light energies. The existence of the subshells was discovered, again, by Schrodinger and de Broglie's work. Yes?
What are the subshells on like the little square diagram you showed?
The subshells are the letters. So, see if I can see if I got a better picture. Oh, get this to go forward.
Those are the orbitals. So that each letter has a certain amount of orbitals.
Each letter is called a subshell, and then each subshell has a specific number of orbitals, yes. So the letters are the subshells, S, P, D, and F.
So the subshells have a certain amount of shells?
The subshells are the letters.
And they have a certain amount of shells.
They have a certain amount of orbitals.
Okay.
Yeah, exactly. And so you could have 4s is a different subshell than 3s because it's got a different energy, even though it's the same spherical shape. Now, in polyelectronic atoms, the difficulty we have is there are repulsion of other electrons, so that's why the Bohr model did not work. The solution is to treat each electron as if it were affected by the net field of charge from the attraction of the nucleus and the repulsion of the electrons. So you've got this cloud of electrons, and in this cloud there might be multiple electrons. If they're near each other, they would do what with their charge? They'd repel. But the nucleus is positively charged, so that's attracting those electrons. So it's getting pulled in, and it's getting repelled by the cloud of electrons, and we'll look at that in more detail. The penetration effect explains why. Okay? So, for example, here, the energy for something that is up here in the P, you start out with, let's say n is 1. This would be 1s. Okay, the energy of 1s is going to be less than the energy of 1p. So the energy goes 1s, 1p, and then it goes 2s. And then here, okay, the energy of the d is greater than the s or the p or the s of the original. And because of these energy changes, because of this pattern that can be seen, this explains why the energies, again, are different because of the repulsion of the electrons and the attraction of the nucleus. So how does the penetration effect work? The outer energy levels penetrate the inner levels, so the repulsion of inner electrons is not totally effective. From most penetration to least penetration, the order is NS, NP, ND, NF within the same energy level. So this is why the levels are not at a perfect same energy, because there is the electrons moving in and out of that sphere. So if you have a 1s here, a 2s, and this is a 2p, for example, the 2p electrons are not just found outside the 1s, they're going inside as well, because they're dumbbell shapes.
So are the electrons like going into the nodes, through the nodes?
They're not going through the nodes necessarily, but if this was a 1s and this was a 2s, for example, sphere, there are nodes in the 2s, and so the electrons wouldn't be found in that space, but they're found inside. They can be found inside exactly where there's overlap.
How do they get there? Because they can't go through the node.
How do they get there? That's a good question.
Isn't there overlap? Well, but there's overlap, but there's a node in the middle where they can't be found.
They can't be found there, but they can be found on this side or this side.
So they're not moving from like.
We don't know.
So.
We don't know how they get from here to here. This is the Heisenberg uncertainty principle. We don't know how they get from here to here, or whether they're traveling in straight lines, or whether they're going in a different way. Yeah. And that's the same with all these pictures. All these pictures, wherever it's not 90%, wherever it's not 90%, we don't expect them to be found there. And the nodes, we know they won't be found there. But that's about all we know for sure. We don't know how they get there. So it's a good question.
Is it 10% and electron goes in the node?
No. Node is, because an electron behaves like a wave, it will not be found at that node.
Question. It can go from one to the other though, but we don't know how.
Correct. If you have a 2, this isn't a great picture, but if you have a 2s, it's hard to draw, but let me see if I can draw it. In a 2s, there is an electron distribution area out here. Okay, and then there is a node here, and then there's electron distribution area in here. If for the 2s, it has a node, so the electrons are not found there. The electrons, the 2 electrons in a 2s could be found in here or in here, in any of those locations, but it's not found in the node. That's what our probability distribution says because it's a standing wave, the way it behaves. How does it get there? Yep, good question.
What do you mean by penetration?
Penetration means that if you have, let me see if I can draw this. If you have an S orbital here, okay, the 1s orbital is smaller than the 2s orbital. Okay? So what that means is the electrons from the 1s will be found in this space 90% of the time. Okay? The electrons from the 2s, they're in a further energy level, but they could be found out here, or they could be found in there as well, because they're both spherical. So they overlap each other, and that penetration means that this electron penetrating the previous shell is what is meant by the penetration effect. So we would think that they would that the energies would match up perfectly with energy levels, but because they do not, this is what gives us our order of orbital filling. The electrons prefer to be in the S and the P versus the D. So this is why we don't want to have an electron going to the D, because of the penetration effect. So this is the explanation for why we got the lines the way we did with multiple electrons. Now, to show this in graphical form, this is what's called the radial probability. So the distance from the nucleus is here, and the probability of finding them is here. So you see our 2p is actually closer to the nucleus than our 2s. 2s, here's this part, there's the node. Look at the node right there. 0% probability. It's not going to be found there. Crazy as it seems. And that's due to the standing wave. And I'm not saying I completely understand standing waves and how they work. I'm not going to even admit it. They're pretty cool that electron does that. I don't know why or how. Yeah.
So it goes from there to there.
So it's either in this space, this distance, or this distance. Most of the time it's around here.
What is penetration from those one line to another?
Penetration would be, this is one orbital here, this is another orbital.
But the electrons
Okay, where they overlap would be considered penetration. They're not separate from each other. The electrons are moving through the other spaces. Okay. Now, if you look at this electron here, this here is part of the penetration. The 2s electrons spend a small but very specific amount of time closer to the nucleus. So 2p we would expect to be further away. This 2s is closer to the nucleus, so this is our penetration effect. The electrons spend some time closer to the nucleus than in the 2p. Okay? And so that is why the energy levels fill up the way they do. That's why the 2s, for example, fills up first with electrons, then the 2p. Even though the 2s electron spends most of their time further from the nucleus than the 2p electrons. So normally they're found further than the nucleus, but sometimes they're found closer. And because of that, it changes our picture of what fills up first. So the energy for the 2s is going to be less than the energy for the 2p because of this little thing here called the penetration effect. So that's why we have a little bit lower 2s and a little bit higher 2p. They're still very, very close, but a little bit of difference. Okay? That means if electrons are going in, it takes less energy for it to be in the 2s than it does for it to be in the 2p. If we look at the 3p, would it have a penetration effect? Yep, because you got this little right here. Sometimes it's spent over here. There's the 3s. Okay. Yeah, so which one? 3s or 3p? That's a... Yeah. And so when you start increasing the energy level, you're going to have more and more nodes. There's a node there, there's a node there. Here, low probability of finding any electrons. Still there, but low. If you got the 3D, look at how the 3D spreads out.
So does that mean just go to 3D first? Because it almost looks like that.
It almost looks like it should. Yeah. What happens is, though, it goes to the 3S first, then it goes to the 3P second, then it goes to the 3D after the 3P. It actually goes even, see if we can have it drawn in there. These are all three, the penetration. The 3S has 2 penetrations. The 3P has 1. So this is why the 3S gets filled up first, the 3P gets filled up second, and then the 3D will get filled up eventually. However, okay, we would think 3S, 3P, 3D. But look, watch what happens. 3D glasses. What's before the 3D? The 4S, the stinking penetration, right there. 4S usually gets filled up first. But you can see their energy spreads are similar in terms of how they're spread. There's a few nodes to the 4S, but it gets filled up first. And the 3D soon after that. So this is why we go 3D, 4S, then 3D. So 1S, 2S, 2P, 3S, 3P, 4S, 3D. 4P then comes next. Then 5S, 5S, 4D, sorry, can't see that. And then it goes up to the 5P and the 6S. So this is the pattern, at least, of how the energy levels are slightly modified. So this electron here, if n equaled 5, L equaled 1, m sub L equaled 0, and m sub S equals -1/2, the electron would be placed here. 5th energy level. If L equals 1, that's the p orbital. If m sub L equals 0, why is it in the middle? -1, 0, +1. And then why is it pointing down? -1/2. So right now you've been able to identify the location of an electron given 4 quantum numbers. Okay, if I gave you a different one, could you identify it? Yeah, takes a little bit of effort, but possibly you could look at your notes and go, okay, all right. What if we had 410 +1/2? +1/2. All right, this box, right, should be going up or down? Up, going up. All right. So now we've been able to identify electrons with incredible specificity. If we had 4, 3, -1, 1/2, it would be right here in the 4F. Okay. So there's our L0, L1, L2, L3. And if we had an electron here, it'd be 3, 2, -2, 1/2 positive. All right, what I'd like you to do at this time is I'd like you to invent a set of numbers for your partner. Okay, write them down and switch papers and see if you can identify where you think the electron would be drawn. Yeah. What type of textbook do you want? You want the AP Chem?
Yeah,
Good. Mm-hmm. Third box. This one here. Okay. So if you're in the F here, you've got 0, positive 1, positive 2, positive 3. For the F, you've got positive 3, positive 2, positive 1, 0, negative 1, negative 2, negative 3 as the M sub L. Correct. Yep. Yeah, that's easy to see. Yep. All right, let's have some fun here. What if we did this one? 7, 0, 0, 1/2.
That's what I did.
Oh, you did that one? Can you tell me where its electron would be? 7s up arrow. Let's see. Yay! And if you did 2, 2 double O negative 1/2, it would be 2s down arrow. Yes, sir. Never mind. All right, now. This puzzle here, next person in our history is Wolfgang Pauli, and I love Pauli. I love the Pauli exclusion principle. It works out great with friends and enemies. Wolfgang Pauli said, no two electrons in an atom can have the same 4 quantum numbers. Whoa, so it can't have all the same numbers? Why not? Why couldn't it have all same 4 numbers? It'd be in the same exact place, facing and spinning in the same exact direction. So Pauli, I love it, because he just totally gave this quantumly advanced explanation. What he really means is, if you're spinning up, you can't have another spinner up. You can't have 2 people sleeping in the same bed, spinning up. What? Oh, no. He didn't say that, did he? No. He said something different. Now, Wolfgang Pauli, was he talking about beds? All right, now. Hopefully not. But the truth is, Wolfgang Pauli was explaining a very common principle. Okay? In my family, there were 3 boys growing up. These are my 2 brothers. Okay? And the great thing about it is when we would go to hotels, there'd be 2 beds. And guess where I would end up sleeping? On the ground. That's because, not the Pauli exclusion principle, but the Christopher exclusion principle said that only 1 male Christopher can sleep in a bed at a time. And if you are forced to sleep in a bed with another male Christopher, you have to face the opposite direction. I don't know why. Some people told me it had to do with spoons and forks and knives. I never understood that. I had no idea what that meant. My brothers would tell me, you can't sleep in here. And I was like, okay, you're bigger than me. So, Pauli did not say that, though. That's the Christopher exclusion theory. Pauli had a real interesting explanation. 1 spinning up, 1 spinning down. They can't both be spinning up. They can't both be spinning down. That's it. Pretty simple. So that means an orbital can hold how many electrons? 2 electrons. This is where the rule came from. And they must have what? Opposite spins. So arrow up, arrow down. There it is. Oh no! Fail. That's totally wrong. What should it be? Up and down. There you go. All right. Now, this is my favorite principle because it's the easiest. It's super easy. But, however, some people decide to do this just for fun, and they get it completely wrong. So, this is the other best principle. This is called the Aufbau principle. Say it with me. Aufbau. Now, if you don't know German, this is German, which basically means building up. Aufbau means to build up. Now, let's see how Aufbau works, because it's even better than the Pauli exclusion principle. Oh my God. As the protons are added, protons, wait a minute. The electrons fill up hydrogen-like orbitals. So as you add more protons and electrons, they fill up the orbitals. They fill up orbitals in order of increasing energy. Oh, so that's why we spend so much time on those energy levels. Because the electrons fill up from the lowest energy to the highest energy. This is the Aufbau principle in a graphic form. Now, you're looking at it and go, what's a lot of letters and numbers? The cool thing is, this is on the table right there. So you don't have to memorize this. Okay? The cool thing about this principle is it's on the table. So, my suggestion is if you want to memorize this picture for fun, you can. I will show you another way of doing it. A little bit easier. But it is based on the energy levels we just saw. Now, we've got the Pauli exclusion principle. We got the Aufbau, which means you go from the closest to the nucleus to the furthest. And we got Hund's rule. Friedrich Hund, 1997. Lived 99 years. Pretty cool. He said the lowest energy configurations for an atom is the one having the maximum number of unpaired electrons, allowed by the Pauli principle in a particular set of degenerate orbitals. Oh, 101, sorry. Hund, of course, would be 101.
Yeah, the irony.
Yeah. The one is an up electron, the 0, and the other one is a down electron. Now, how does Hund's rule apply? The electrons want elbow room. This applies to the Christopher exclusion principle. Okay, you want elbow room. You want to sleep in a big bed. So you kick your little brother out. So if each of these represents a bed, boop, boop, boop. Okay, electrons do not want to be in the same bed if they don't have to be. They don't want to pair up like this if there's 2 extra beds. Okay, if there's 2 extra beds, you want that room. So this person would fail if you paired them up. Instead, what happens is the first one goes to the first bed, the second one walks in the room, and goes into the second bed. Facing the same direction, of course, so they can have a conversation. But, I'm sorry, that's Christopher rule, not Hund's rule. But they are facing the same direction as what you would enter them in as. Yes, sir? They are put in with the same spin. This is Hund's rule. Doesn't necessarily mean that's exactly what happens, but that's the rule. It also makes it easier when you're drawing up arrows to keep drawing up arrows instead of having to flip back and forth. It's just a convenience. But that's Hund rule. Now, rules for filling orbitals. First rule is lowest energy orbitals are filled first. Yeah.
So for the last one, if you had another electron, you could put it in and it would be in the third box that's still going up.
Yep.
And then if you had a fourth, you'd have to put it in one of the boxes going down.
First box.
First box? Okay.
That's the Aufbau principle.
Okay.
Yeah. So Aufbau kind of said that, okay, yeah, we know 5P, they're all the same energy, but Aufbau principle is you build it up. So in terms of energy, we can think of it going this way, higher energy, lower energy, if you want to think of it in that way. So the first rule is lowest energy orbitals are filled first. Okay, this is the Aufbau principle. Only 2 electrons of opposite spin allowed in each orbital box. When filling subshells, fill each orbital with 1 electron spinning up, and then add 1 electron spinning down only where necessary. So this is the Hund's rule, Pauli exclusion principle, and the Aufbau principle, all combined. 3 principles for one way of drawing a picture of the electrons. Yes, we will show you. How many electrons do we put in? Do we put in 1, 2, 7, how many? Yeah, exactly. And that comes from the atom you're looking at. We'll get right there real quick. So, P is an atom. Okay, it's a P break. If you have to go, just raise your hand. P is an atom, though. For an orbital diagram of P, the first thing we look at is P. That's how many total electrons? 15 total electrons. So we're going to be placing 15 arrows. Okay? So, first question, how many electrons does it have? It's got 15. So, we have a drawn orbital diagram. This is an orbital diagram, and then we distribute electrons according to the rules. So where does the first one go? 1s up. Second one goes 1s down. We've placed 2 out of 15, so we've got 13 left. Where did the next one go? 2s up, and then 2s down. Okay, we've got 11 left. Where do they go now? 2p. So 2p, where does it go? It's got to go up, up, up. And then it goes what? Down, down, down. Okay. So now we've got 2, 4, 6, 8, 10, 12. We have 3 more left. Where do they go? 3p, but they all have to be up. If one of them is down, it's wrong. If one of them is paired up, it's wrong. If 2 of them are paired up, it's wrong. If all 3 hop into a container, it's totally wrong. Any questions? This is how to draw an orbital diagram. People ask, will this be on the AP test? They could definitely do this. Yeah. You go to 4s, then you go to 3d, then you go to 4p. Yes, sir. 16, you would put another one in here, yes. Because it's easier for them to be at this energy level than to go up in energy level. So it's easier for them to pair up than to jump up to another level. Lazy electrons. All right, let's try this one here. All right, P3 negative. Okay, phosphide ion. How many electrons does it have? 18 instead of 15. Why does it have 3 more electrons? Okay, -3 charge. So what do we do with this diagram? Do we erase or add? Right? And where do we add them? 3p, just like that. They pair up.
Oh no.
It now has 18 electrons. What element has 18 electrons besides phosphide ion? Argon does. So it has the same number of electrons as argon. All right, let's try for francium. 87, is that high enough for you? Somebody wanted a bigger number? All right, so you don't have to draw this out. This is the Bohr model with all the circles drawn in the middle. Took me hours to paste this off the internet.
Hours upon hours.
Hours. But as you can see, here's our entire orbital diagram. We start filling them up one by one. 1s, 2s, 2p. What comes next? 3s. Then what? Then what? 4s. What comes after 4s? What comes after 3d? 4 what? 4p. Don't go up to 5. 4p. What comes after 4p? Are you sure? What about the 4d? It looks like it's pretty low. No. 5s. And then what? And then what? 5p. Ooh. Now it's tricky. Goes to 6s. And then 4f. Why? Has to do with the penetration effect. The energy of the 4f is actually lower, a little bit higher than the 4d. And then after 4f comes what? 5d. Now I don't even know how many electrons we have in here, but we got a lot of them. Oh, 7s. And there's 1 electron in the 7s. What row is the francium in? What row? 7 right there. So this position is also known as the 7s1 position. Now, orbital diagram practice. If you'd like to go home and play with these, this is a cool interactive. Allows you to practice doing these over and over and over again. So, if we've got a orbital diagram, electron configuration is just you write the N and the letter of the lowest energy subshell. So, the first thing you do, then you write the number of electrons in the subshell as a superscript. Then you repeat for each successive subshell for all electrons. So you start just the way you filled it up. The first energy level is what? 1. And it's 1 what? 1s. And how many electrons are in there? 2. So that's 1s2. Next level is 2s. And there's 2. Then you go to the 2p. How many electrons are in the 2p? 6. How many are in the 3s? 2. Then the 3p3. That's the electron configuration of phosphorus. Right? So what I'd like you to do is we've drawn a modified orbital diagram here. Using this picture here, I'd like you to fill in the orbital diagram for each of these elements. Then I would like you to write their electron configuration next to it. Okay, you have about 3 minutes to fill that in. I would take out a single sheet of paper, just write the element, orbital diagram, and then electron configuration. Would you like to do the first one together? Yes. All right. So if you're not interested in doing this with me, please be quiet and talk to yourself outside, or be quiet. Or if you're not being quiet, be quiet. If you are listening, you can just look up here. Boron, it's got 5 total electrons. So the 1s is the lowest orbital of energy. One goes up, and the other goes down. Then it goes to the 2s. You've placed 2 out of the 5 electrons, so I got 3 left. One goes up, one goes down. I got 1 more electron left. I place it up in the 2p. For the electron configuration, I've got 1s is filled with 2 electrons, 2s is filled with 2 electrons, and 2p has 1 electron. So that's how to do boron. I chose elements near the top of the table, so this doesn't take us an hour. But if you want to have really a lot of fun, do the electron configuration for uranium. It's a blast. And for those of you that are not doing this on a piece of paper, I will ask you to do the electron configuration for uranium, whether you know how to do it or not. Maybe an orbital diagram for uranium too. Do it at home for extra credit. You can do it at home. If it only lost 1, it'd be like beryllium. That's not enough again. Beryllium is more reactive than boron. That's more of electrons. Why is it more reactive would be the next question. Yeah. After 3s is 3p. 4s, 3d. After 4s, you get the 3d. All right, let's look at carbon. So for carbon, we've got 6 electrons. Up, down, up, down, right?
Yeah.
No, not up, down. Up, up. They don't want to be in the same orbital unless they absolutely have to. Why? That's due to Hund's rule and the Pauli exclusion principle. They do not want to be in the same orbital with the same, opposite spins unless they have to. So this is 1s2, 2s2, 2p2. Now, to double check if I have the right configuration, you just add up the small numbers. It should equal the number of electrons. So if you made a mistake and you got 8 here, then you can go back and fix it. Okay? For sodium, down at the bottom, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1s2, 2s2, 2p6, 3s1. Neon is going to be only 10, so it's going to be very similar. What's different about the two of them? The 3s. Now, the interesting thing is sodium. If sodium becomes an ion, what does it become? Na+. So if it loses one electron, if it loses that one electron right here, it becomes 1s2, 2s2, 2p6. Its electron configuration becomes like neon. Is it actually neon? No. But its electron configuration becomes like neon. And this is called isoelectronic. The reason ions form is so that their electron configuration will be like a noble gas. This is why most chemical bonding occurs. Want it to become like a noble gas. So if we put in nitrogen, 1, 2, 3, 4, 5, 6, 7. Nitrogen here is 1s2, 2s2, 2p3. So that's how to do electron configuration of the elements. This is how we can keep track of the electrons. Now the 2s and 2p area, if we change our color to purple, because I like purple. Okay, 1s has one shell and one subshell. 2s has two subshells. These two areas are called the subshells. 3, the third energy level, is going to have how many subshells? 3 subshells. 3s, 3p, and 3d. So some interesting thing happens as you get past the 3s, which we'll talk about here. So for francium, to write the electron configuration of francium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and then 6s2. And there's more. 4f14, 5d10, 6p6, and 7s1. So in general, you'll notice S's come first. S, S, P, S, P, S. Then the D gets stuck in here. For D, the D is one less. The D is one less than the 4. Here, the F, the number is how many less? 6 is how much more than 4? 2. So the difference here is a 2 difference when you get to the 6s. So here are the orbital diagrams for common elements that we just filled in. Oh, sorry. The international community recommends this periodic table here. You'll notice that the numbers go across 1, 2, 3, 4, 5, 12, 13, 14, 15, 16, 17, 18. You'll notice that this color here is purple. What else is purple? Helium. They actually recommend that this helium should be over there. Seems to make sense. It looks like it has a home there. But it's a noble gas. So we got a little bit of a problem here. In here we see all of these fit together, all of these fit together, and all of those are the same color here. So this form of the periodic table relates to the subshells and the shells. So if you look here, elements position in the table reflects how many electrons are in the highest energy subshell. So magnesium, if you're at magnesium, the very last subshell is going to be 3s2. If you're at chlorine, the last subshell is going to be 3p what? 5. If you're at helium, it's going to be what? 1s2. Now, if we're writing the electron configuration for argon, for example, Ar, it's 3p6. But we have to do first 1s2, 2s2, 2p6, 3s2, and 3p6. We have to fill up everything before it, right? If we just wrote that argon was 3p6, would that be enough electrons? 6 electrons for argon? No, it's not representing all the electrons. Okay, so that is how the electron configuration can help us. Details about electron configuration. Elements in the same column have similar electron configurations. Put in columns because of similar properties by Mendeleev first. Similar properties because of electron configuration. Noble gases have filled energy levels. So their energy levels are completely filled, and this is what gives them their stability. Transition metals are filling the d orbitals. So here's our 1s, 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 3d, 4d, 5d, 6d, and 4f and 5f down at the bottom. So some things to etch in your brain. A lot of people forget this. The n here is just the row you are on. There's row 1, 2, 3, 4, 5, 6, 7, 8. So the periodic table, if you look on the periodic table, it has period. That's the row you're in. N equals 1, n equals 2, n equals 3, 4, 5, 6, 7. So that's already on your periodic table. Although it is something to remember. Hopefully you won't forget. 1, 2, 3, 4, 5, 6, 7. The thing that's tricky about these here, okay, this is actually in row 6. If you follow it down, 57, 58. It's in row 6 on the periodic table. When it's in row 6, what you do is you change the number from 6 and you subtract 2 from it. So what's 6 minus 2? 4. So these are the 4f's. 7 minus 2 is going to be the what? 5f's. 5f's. The D ones are also D. Okay, D stands for what? Yeah, not dumbbell, but diffuse. Sometimes I say D stands for different because you take the n value, this is n equals 4, you subtract 1 from it. So this is going to be 3D here. This is going to be 4D here. This is going to be 5D. This is going to be what? 6D.
So it's 4f before 5d.
Is 4f before 5d? 4f is before 5d in most people's explanation of this. We will fill it accordingly. The other thing is helium is over here next to hydrogen. Okay, so these are the F's down here. These are the S's up here. Over here, this block is called the P block, and the transition metals are called the D block. D stands for diffuse, but sometimes I think of it as different. The D block is different. It is not the same in terms of its number. And then the F block, well, that's really F indifferent. N minus 2. That's the way I remember it. It makes it easy. And oh my gosh. So, the next thing to look at is the pattern. This is S1, this is S2. These are all the D, which are N minus 1. D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. And the last one are the P's, P1 through P6. Okay? Now, a little bit of practice to help us out. This is like a code. So this code right here, see if I can make it an arrow. If we look at aluminum here, its code, okay, the very last part of the electron configuration of aluminum. What row is aluminum in? Third row. And what subshell? S, P, D, or F? P. And is it the first, second, third? Whoop. It is the first one in there. Let me see if I can get this arrow right back. It is the first one in here. So its code for aluminum should be 3P1. What would the code be for bromine here? 4P5. What about potassium? Or S1. What about cesium? Cesium, CS? 6S1. What about astatine? 6P5. Now, what you are identifying is the very last part of the electron configuration. Everything before it is going to be completely filled up. Okay? So, since everything else is going to be filled up completely, okay, this information to help us lock this in our brain, to help us lock this in our brain, we're going to be practicing with this in just a moment. So, for Bi, I'd like you to write the electron configuration for Bi. So, Bi, you tell me what to write. I'll write it for you if you want to do this together. Bi is 83. So 1s2, thank you. What comes next? 2s2, what's next? Next? Okay, next? Okay, next? 4s2, very good. Now we got a weird one. We got the D's. 3D? How many? 10, all 10. Okay, after the 3Ds comes the 4p6. Then what? 5s2. 10, and that means we're right about here right now. Right there. That's where we're at. So we still got a ways more to go. So after that comes 5p6. 6s2. 4f14, very good. What comes after the 4f14? 5D10, and then the 6p6. That leaves us at Z. Where are we at? Oh, is it 6p6? All right, we went too far, huh? 6p what? 6p3, very good, and that is our 6p3, our bismuth. That's the number one error on electron configurations, is just going too far. Okay? Now, there are some exceptions, of course. Now, there are some variations. Okay, the way it's written here, they all end as 6p3, but you'll notice here they're written differently. Okay, this is going 6 to 4 to 5 to 6. Okay, this one here is going 5 to 4 to 5 to 6 to 6. This one here is separating out the 1, the 2, the 3, the 4, the 5, and the 6. Okay, this here is the most widely accepted electron configuration. These here give information in not a energetic form. So it's not based on the energy levels exactly. Okay? So this here is the one that we will be using. You may see one or more of these online. Different people use them. The AP exam looks at this configuration here. Now, the shorthand, because it gets so tiring writing the entire electron configuration. Okay? Well, actually, we shouldn't learn this yet. You want to take a 20-minute break?
I like that.
I thought we should play a game.
Heads up, 7 up.
We were going to play a game.
Heads up, 7 up.
Like heads up, like the arrow and then 7. Like 7 is an important number, and heads up, like to learn about
It's
the
a fun game, right? No, I wanted to watch it great too. What game are we going to play? All right. So we got choice. Okay, we can learn the shorthand right now, or we can play a game. So, shorthand, shortcut. Shortcut. Game. All right. All right. Game. All right. So we saw late vote. All right. So a couple people wanted to work on labs too. So let me see if we can work on the shorthand really quickly. Shortcut. First of all, if it asks you to write the entire electron configuration, you'd write out the whole thing. If it doesn't ask you for the entire thing, use the shorthand. So tin has 50 electrons. So we could go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p10, 4p6, 5s2, 4d10, 5p6. Oh no, 5p2. Now we could do that. Or we could use the shorthand. The noble gas before it. What's the noble gas for tin? It's Kr, krypton. So, we write this in a bracket. Kr is the previous noble gas. Here's Sn. Kr. Previous noble gas. Previous noble gas. This takes care of 36 electrons. So the bracket says this is the electron configuration of Kr. Everything that I didn't write is there. It's a shorthand. So this says it's the same electron configuration as Kr up to that point. Then we start filling them in. The next is the 5s2. Then you got your 4d10, which is all 10 of those. And then the next ones, we've got 2. What is that going to be? 5p2. So that is the electron configuration of tin using shorthand. Okay? So that makes it easier, especially for the big ones.
Wait, what was that?
Now, this here is another way of arranging it. The thing that's unique about tin, tin tends to have a positive 4 charge, right? Or a positive 2. So if we think about this, it can either lose 4 or 2 electrons. But it has 14 here. So which 4 do you think it would lose first? 5p2 and 5s2, because they have at the highest energy level. 4d is at a lower energy level, even though it's written second, which is kind of confusing sometimes. So these two, those 4 electrons are usually given up. That's what tin, when tin becomes a +4 ion or 4+ ion. So you identify the group 18 element, preceding it, you put it in brackets. You have the remaining portion of the electron configuration. So bismuth, here's the big old long thing we just wrote out. Break it down is the one before bismuth. Xenon, that's at the end of the 5p. So everything up to this 5p turns into xenon. So that whole thing is Xe, bracket it. And then 6s2, 4f14, 5d10, 6p3. Now, if you look at the ones with the largest numbers up here. Largest numbers. How many electrons are in the ones with the largest numbers?
14.
Largest big numbers, sorry. There are 3 here. And 2. So we can think of bismuth as having 5 possible electrons. 5 possible electrons that could be lost or possibly gained, depending on what happens with bismuth. So the electron configuration gives us a lot of information about the sample. Now, valence electrons are electrons that are furthest from the nucleus. Okay, these are the electrons I was just identifying. They're called valence electrons. They're in the highest energy S and P shells, but not the D. Or that. Because D and F are going to be a lower energy level anyway, so you don't really have to remember that. Just look at the big number. The big number, I'll give you valence electrons. The electron that determines the certain chemical properties. Valence electrons are also the electrons involved in chemical bonding. So I mentioned tin. To lose 4 electrons, those are its 4 valence electrons. Okay. Tin, you'll notice, is in this column. Silicon also has 4 valence electrons. So does germanium. So does lead. So does carbon. They have a similar pattern because of their electron configuration. How many electrons, valence electrons, does bismuth have? 5. We learned that from the electron configuration. Is there an easier way of determining it? Yep. You look up here. What's it say? 5A. You're done.
Oh, that's cool.
And Americans did that intentionally. They put a 5A. The international community wants it to be 15. So you just have to subtract 10 from it if you want it to be that way. The A's up here tell us the number of valence electrons. Almost all the time, but not always. Okay? So, valence electrons in bismuth are these 2, the 6s and the 6p. All the rest are still inside. They're not available for bonding. So, bismuth has 5 valence electrons. Now, core electrons. This is the most easiest concept ever. Okay? Valence electrons. You got bismuth has 5 valence electrons, right?
Yes.
How many electrons total does bismuth have?
83.
83. What's 83 minus 5? 78. That's its core. That's it. Everything other than valence is core. Okay? They are also the inner electrons that repel the valence electrons, and they are not involved in chemical bonding. So bismuth, we got the answer already. We already did our math, 78. Right? That's it. Very easy to calculate. You do have to remember that they do repel the valence electrons. Because they're negatively charged, the valence electrons are negatively charged, they repel one another. Okay? So here are the electron configurations broken up into columns. You notice something similar about all the alkali earth metals. They're all S what? Alkaline earth metals. S2. Noble gases are all what? Most of them are P6 with an S2, except helium. Alkaline metals are all the S1s there. So, some broad periodic table classifications. Representative elements, main group, filling S and P orbitals. Transition elements are always the D orbitals. Lanthanide and actinides are the F orbitals. Electron configuration and stability. Stability means the lowest amount of potential energy. So, we just saw this. In order for an element to become an ion, it has to lose or gain electrons. The electron configuration with the highest N sub S, NS, and NP subshells is the most stable. So you want to completely fill up, if you can, the S and P. The noble gases are the ones that are completely filled up. They are the most stable. All other elements are not stable. So they will tend to lose or gain electrons to become like a noble gas. They will also participate in chemical reactions, losing and gaining electrons to get a full NS and NP subshell. Now, if you look at nitrogen, nitrogen will want to gain how many electrons to be like neon? 1, 2, 3. What if it lost electrons? How would it become like helium? How many would it have to lose? 5. So the question is, gain 3 or lose 5? What's easier to do? Okay, gain just 3. Okay, the less movement of electrons, the easier it is to do. That's how you can predict. You wouldn't have that situation, fortunately. Gain and lose 4, you could have that situation. And they tend to lose because they become metals. So carbon is one exception to that. Yep.
What about the like tin, 2, and 4, the ones that have 2 options?
Uh-huh.
How do you know which one they're going to do?
That is a little harder to predict which one they're going to do, but the reason why, for tin or lead, tin is 5s2. So tin has these valence electrons. Okay? There are 4 total. If it loses just the ones from a p, it loses 2. If it loses just the ones from the s, it loses 2. If it loses all of them, it loses 4. Tends to be, although if it loses all 4, it would be like a noble gas. If it loses only 2, it's just going to be like strontium, which isn't as stable. So it would want to lose all 4 if possible, but it takes more energy to lose all 4. So it's a trade-off. Lose a little bit of energy, 2 get gone. Lose a lot of energy, all 4 get gone, but then it's more stable. So there's an energy transformation. How to predict it? That's very difficult to do. You'd have to know energies and what you're adding into the system. It's possible to do, but not impossible. All right, now, at the beginning of the year, we talked about ions. You guys have memorized a lot of ions. Where did those things come from? Okay? All of the ones in the alkali metals, the reason they all become +1 is they all want to lose 1 electron. They want to be like a noble gas. These all want to lose how many electrons? 2. To be +2. These want to lose how many? 3 to become 3+. These want to gain 2, and these want to gain 1. Okay? Now, you might ask, well, what about these in here? Yeah, what happens with those? Those are, again, harder to predict. Okay, you've got tin and lead and lead and carbon. You got all of them in there. Lin and Ted. All right. Transition metal cations. Someone was asking, what about my transition metals? I love them. They have various chargeables possible. Because what happens is they're removed from the S first and then from the D. So you have various choices. That's why you can have copper +1, copper 2+. You could have iron 2+ and iron 3+. And that's based on their electron configuration. Let me see if I have a slide on that. Okay, noble gases and halogens. Noble gases are incredibly stable. Halogens are incredibly reactive. Fluorine is one of the most reactive elements on the periodic table because it wants to steal 1 electron or take 1 electron to become like argon. Now, what happens with the alkali metals? I lied to you? The game takes too long. You wouldn't want to play it today. It's a really good game. It's a great game. You'll love it. You're going to love it. The game is Battleship. All right. So I don't want to be a liar. So what you're going to do is in your lab manual. All right, in your lab manual, you're going to look for a page that looks like okay, it looks like this. Battleship board. There are 2 boards here. All right, for Battleship, this here is our oceans.
That's a very oddly shaped.
Yes, there is a slight land bridge in between the 2 small oceans. This is your fleet. Now, your fleet is going to be 3 P-boats. The P-boats will be 3 squares long. You'll have 2 D-boats. Each D-boat will be... And your F-boat. Hey, no yelling, you sunk my effing boat, okay? All right. I know somebody will do that, it's happened before. All right, so P, D, and F. Now, you've got a total of 5 boats. What you're going to do in the next couple minutes is you're going to find an enemy. Then, all right. If you're not listening, you'll lose the game. It's okay, it's with me. I don't mind. Yeah, I would say you're losers, but that would not be politically correct. All right. Now, you're going to fill in your boats onto one of these 2. Okay, there's 2 battleship boards. One will be for your first game, and one will be for your second game. So, what's going to happen is you're going to, tonight, and in the next 4 minutes, draw in your boats. You do not want your enemy to see it. You probably don't want your friend's enemy to see it either. Your enemy of your friend, or your friend of your friend is your enemy. So, that makes it 0. Friend of your friend is your enemy. Now, battleship is a lot of fun. The way the game is going to be played is after you place your boats. Okay, there's no rules except you can't have a submarine going under the water. You can't have it going diagonally. Oh yeah, I have to show you guys this. I made this just for you. Cheaters. Okay, you could place the boats like this if you wanted to. You cannot place them like this. Okay? That's a P-boat here. 1, 2, 3. You can't do that. You can't put a P-boat here. 1 piece there and 2 pieces down there. You can't put it diagonal. Why not? Because the battleship board is drawn the way it is. You can't put 2 boats in the same space. That's a violation as well. Now, once you place your boats, we're going to be firing at each other using electron configuration coordinates. 5s2, and you would either say hit or miss.
Very insightful.
Ah. 5, and this is the S block, S2. 5p6 would be over there, and so on and so forth. So if you know the coordinates better than your opponent, you'll win.
Can you go back to how we put them in? We get 3 P's out next to each other.
You can put them anywhere you want as long as you don't do these violations here. You can have the boats anywhere you want. 5s2 is because it's in the 5th row. This is the S block here, and it's the second square. This would be 4D1. That's the stuff we have to etch in our brain to play the game. All right, so etch the code in your brain. We'll see you tomorrow for Battleship. We will have 2 rounds, so we'll have a winner's bracket and a loser's bracket. So if you win, you go on. If you cheat, you lose, just so you know.
I have no idea what that means at all.
here.
Part that annoys
You can take